Download this code from codegive.com, link in the description below. OK, let's dive into a detailed tutorial on fitting a first order plus dead time (FOPD) model to your data. This is a common technique in process control for approximating the dynamic behavior of a system. We'll break down the process into 7 steps with code examples, using Python, as it's a versatile and widely used language. Introduction: the FOPD model. The FOPD model is a simple, yet powerful, transfer function representation of a dynamic system. It describes how the output of a system responds to a change in the input, also known as a step change. The FOPD model is described by the following equation, where *g, s transfer function of the system, *kp process gain, change in output / change in input at steady state, *tau time constant, the time it takes for the output to reach 63.2% of its final value, *theta dead time, or delay, the time before the output starts to respond to the input change, *s Laplace variable. The key is to determine kp, tau, and theta that best fit your experimental data. Here's our 7-step process. 1. Data acquisition and preparation. Objective gather the process input, manipulated variable, MV, and output, controlled variable, CV, data. Clean and prepare the data for analysis. Description you'll need to perform a step change in the input of your system and record the resulting output response. This can be done experimentally or using simulation. Data requirements you need time series data for both the input and output. This data must cover a stable initial steady state, a step change in the input, the transient period after the step change, a final, stable steady state, data cleaning noise reduction apply a smoothing filter, example moving average, Savitsky-Golay, to reduce noise in your data. Outlier removal identify and remove any outliers that could distort your model fitting. Data alignment ensure that the input and output data are aligned in time. Code example, Python with NumPy and SciPy. 2. Identify the step change. Objective locate the precise time at which the step change in the input occurred. Description you can do this by visually inspecting the input data or by using an algorithm to detect the abrupt change in the input signal. A simple approach is to calculate the difference between consecutive input values and find the index where the difference exceeds a certain threshold. Code example 3. Determine initial and final steady states. Objective determine the values of the input and output signals before and after the step change. These values are needed to calculate the gain, Kp. Description initial steady state calculate the average value of the output before the step change. Use some points before the step. Final steady state calculate the average value of the output after the transient period has subsided and the output has reached a new steady state. Input change determine the magnitude of the step change in the input, final input value, initial input value. Code example 4. Calculate the process gain, Kp. Objective calculate the gain, Kp, of the system, which represents the ratio of the change in the output to the change in the input. Description Kp equals, change in output, / change in input, equals, output _ final, output _ initial, / input underscore final, input underscore initial. Asterisk code example asterisk. 5. Estimate the dead time, theta. Asterisk objective asterisk estimate the dead time, theta, which is the time delay between the step change in the input and the initial response of the output. Asterisk description asterisk. Asterisk visual inspection asterisk look at the output data and identify the time when the output starts to deviate from its initial steady state value after the step change in the input. Asterisk threshold method asterisk set a small threshold, example 5% of the total output change. Find the first time point after the step change where the output exceeds this threshold. Asterisk tangential method, more accurate, draw a tangent line to the output curve at the point of maximum slope, inflection point. The intersection of this tangent line with the initial steady state value gives an estimate of the dead time. Asterisk code example, threshold method. 6. Estimate the time constant, tau. Asterisk objective asterisk estimate the time constant, tau, which represents the time it takes for the output to reach 63.2% of its final value after the dead time. Asterisk description asterisk. 1. Calculate the 63.2% value asterisk output underscore 63 equals output underscore initial plus 0.632 asterisk, output underscore final, output underscore initial. 2. Find the time asterisk find the time at which the output reaches the 63.2% value after the dead time has elapsed. 3. Calculate tau asterisk tau equals time, at 63.2% value, time of step change plus dead time. Asterisk code example asterisk. 7. Model validation and refinement. Asterisk objective asterisk validate the fitted FOPD model by comparing its predicted output to the actual output data. Refine the model parameters if necessary. Asterisk description asterisk. 1. Simulate the FOPD response asterisk use the estimated Kp, tau, and theta values to simulate the FOPD model's response to the step change. You can do this by numerically solving the differential equation that corresponds to the FOPD transfer function or by using a discrete time approximation. 2. Compare predicted versus actual asterisk plot the predicted output alongside the actual output data. Visually assess the goodness of fit. 3. Calculate error metrics asterisk calculate error metrics such as mean squared error, MSE, root mean squared error, RMSE, or mean absolute error, MAE, to quantify the difference between the predicted and actual outputs. 4. Optimization, refinement if the fit is not satisfactory, use optimization algorithms, example scipy.optimize.minimize, to find the values of Kp, tau, and theta that minimize the chosen error metric. You would define an objective function that calculates the error between the model prediction and the actual data, and then use the optimizer to find the parameters that minimize this error. Asterisk code example, simulation and validation. Code example, optimization. Important considerations asterisk. Asterisk data quality asterisk the accuracy of your FOPD model depends heavily on the quality of your data. Minimize noise, remove outliers, and ensure proper data alignment. Asterisk model limitations asterisk the FOPD model is an approximation. It may not accurately represent complex systems with nonlinear behavior or higher order dynamics. For complex systems, consider using higher order models or other system identification techniques. Asterisk parameter estimation methods asterisk the methods described above are just starting points. More sophisticated parameter estimation techniques, such as recursive least squares or subspace identification methods, may be needed for more accurate models. Asterisk units asterisk be consistent with your units throughout the process. Ensure that the time units for tau and theta match the time units of your data. Experiment design. The design of your step test can significantly impact the accuracy of the identified model. Make sure the step change is large enough to elicit a clear response, but not so large that it drives the system into a nonlinear region. Alternative estimation techniques. Area method. Relates area between the step response and final value of step response. Sundaresan and Krishnaswamy's method. Based on 3 measurements from the step response curve and algebraic equations. This comprehensive tutorial provides a solid foundation for fitting FOPD models to your data. Remember to adapt the code examples and techniques to the specifics of your application. Good luck.